document camera. There it is, hiding underneath. Okay. I'd like to teach you a little bit about static friction, because I know that's something I haven't really mentioned very much. Static friction, different than sliding friction, different than kinetic friction. Static friction. So static friction is a frictional effect that usually it's preventing motion, but not always. I shouldn't say that. Sometimes it prevents something from moving. Other times it actually propels something forward. And I know that at first glance it seems confusing, seems to contradict each other. But friction is a very multifaceted natural occurrence that can do a lot of different things for you. It can provide forces in a lot of different directions, even sometimes simultaneously. Some of them will promote your motion and move you forward, and some of them might end up resisting your motion and slowing you down. All of the frictional effects that we talk about, which is either static friction or sliding friction, again, occur due to the just irregularities. Like I did teach you about the irregularities in all surfaces. There's nothing perfectly smooth, and when one thing that has some sort of irregular surface like that interacts and has something else that's also has something that's rough, and that's of course exaggerated, but at the molecular scale, or at least on the smallest and a very micro, I shouldn't say molecular scale, but certainly on a microscopic scale, you would see that those ridges and bumps kind of lock into place and they kind of fit in. Not all of them do, right? In some cases, you'll probably have, let's just really exaggerate that, one bump that kind of sits on top of another bump. That wouldn't provide any locking mechanism, right? But if you were to able to scan all of those irregularities and see, oh, but look at that one right there fits in really nice. Or even to do it a little different, where this is some surface and this is some bump on a microscopic scale that you're seeing, and you see that the thing that's sitting on top of it has something, again, that kind of fits right into it like that. And if there's millions of these, upon millions of them in a small area, there's going to be some amount that do lock in like that. And if you decided that you were going to come over and try to push this object in this direction, you're going to have to deal with this section, because that section essentially has a hill that it has to get over. And well, it takes force to move things over hills. Even microscopic hills, they're still hills. And you'd say, yeah, it's a small amount of force. I'd say, yeah, but it's a small amount of force per one of these, and there's 3 trillion of them in that one spot. Oh, it adds up. Yep, you're right, it adds up. It adds up quite a bit. And especially when things are rougher than other things, that two rough surfaces that texturally are rough, you can really have some serious, significant locking mechanisms that are happening that you would feel when you tried to push this, because it won't move. Most people would say it's because it's too heavy. No, heavy goes this way. Heavy works in the downward direction, because when people say heavy, they're referring to gravity. Sideways forces and vertical forces are like apples and oranges. They're both fruits, but they're very different. Forces in the vertical direction and forces in the sideways horizontal direction are both forces, but they're very, very different. They don't ever fight against each other. Just doesn't work that way. Wish I had some way of, sorry, I'm dealing with this. Maybe I'll shove it in here. Just keep slipping. Right there. It's too loud. A little better, a little better. All right. So what I'm saying to you is that when you are looking at typical diagrams, like in not my little crazy pictures I just drew, but like AP level, with the way they draw it, they would usually show some force like this, and they put F. That's indicating that there's some sort of force being applied, an applied force. They actually don't usually say FA, but in colleges, almost all professors would put FA to indicate it's an applied force. But in College Board, for whatever reason, they just put F. And then in the sentence, they'd say there's an applied force, so you see that they're mentioning it, but when you look at the diagram, you just see F. if it's not moving, if this force does not cause motion, and you have surely gone over to something at some point in your life and tried to push it sideways and said, it's not budging. Probably many times over, starting when you were a kid. If this force does not cause motion, then what is the net force? If this force does not cause motion, what would the net force be? There are forces. Somebody's sitting there pushing on it, and it's not causing motion. What is the acceleration of something that's not moving? If it does not cause motion, that means the acceleration is zero. The horizontal acceleration is zero. And Isaac Newton said, well, if something is not accelerating, then the forces must be balanced. Balanced forces means there's zero net force. The net force is 0 newtons. Well, we already know that the normal force coming up in this upward direction like this from the floor is balanced with the gravity force down. We've seen and heard that 1,000 times at this point. So I think most students are probably good with that. But we're not talking about the balanced vertical forces, which again, we're aware of. This force that we're talking about, again, that is being applied to try to move it to the right, must be balanced with a force in which direction? Just like the normal force must be, which is up, must be balanced with a force that's down. An equal amount of force, but opposite direction. Not any more, not any less, because then it wouldn't be balanced. It has to be the same amount of force, but in the opposite direction. Now let's apply that same thinking to the horizontal direction. A force is being applied to the right, and it's not moving. How much force must there be on this block to the left? You'd say there's an equal amount of force, right? An equal amount of force, and we would write FS to indicate that in a diagram, where S stands for static friction, the little f stands for friction, the capital F stands for force, and when we see that, we say the force of static friction, FFF. You know, when we talk like that as scientists and engineers, if people heard that FFS, what the heck are you talking about? Well, that's our language. That's how we talk to each other. FFS, somebody would, oh, that's the force of static friction. I mean, they could say the words, but you know, sometimes people would refer to it literally as that if they're referencing math, stuff that's math. So my point is that if I drew a free body diagram for the scenario, the normal force is up, the gravity force is down. The force being applied to the right might be called F, while there's a frictional force preventing this thing from moving, the snagging effect, like I told you, in those little holes and little hills, there's a snagging effect. It snags, it catches. And that's providing a resisting force, saying you're not going to move this to the right unless you're strong enough to overcome me. And that's what we're going to talk about in a moment. This would be FFF. All right, so this means the net y component forces add up to 0, and it means that the net x component forces add up to 0. And if that's true, if forces are balanced in all directions, then we can just say the net force in general, in total, as a vector, must be 0. Because F net as a full vector has to be thought of in terms of the two pieces, the x forces and the y forces, right? So you might say, yeah, well, if something was strong enough, it'll make it move. It just, maybe you're not strong enough. Hey, Bob, come on over. Help me push this. All right, so now Bob's pushing with you. Of course, the rightward force will increase because both of you are pushing to the right. Mathematically, those would be represented as two positive signs if they're both to the right, or two negative signs if they're both to the left, because they are on the same team after all. And two negative numbers become just a larger negative number, more force to the left. Or to the right, it would be two forces to the right add up to make a larger rightward force in total, right? At some point, it slips. If there's enough force between you and Bob, at some point, you're going to be strong enough to push it over these hills, these little microscopic hills, and you're going to be able to break that force. Think of it as like glue. It's not glue, but if you want to think of it as glue, if you're strong enough, you can eventually break that bond. You can snap that bond and motion occurs, right? And so this is an important part. There is a maximum, because this is usually what the AP exam refers to when they decide to give you a static friction problem. Usually it's in reference to this maximum amount of force that static friction can use to prevent the motion. So there is a maximum amount of static friction force occurring underneath all objects. I mean, it doesn't have to be underneath. Most things are, in a normal world are standing upright, and usually you'd be referring to the stuff that's the area underneath. Technically, could they give you, a wall problem where the block is, and they do sometimes, being pressed against the wall? And they say, you're pressing this block against the wall and it's not moving. Well, then you'd say, well, where's the static friction force happening? Underneath. Well, where is underneath? Underneath is actually in this area. So in those weird examples, yeah, it's, maybe not, you wouldn't think of it as underneath. But 99% of the time, in our normal world, you think of it as being underneath. There's a maximum amount of static friction force occurring underneath any object. Which is equal to so we usually use all of those notations, F, F, S, max. The force of static friction, but the maximum force of static friction. It's something you have to be stronger than if you want to make it move. It's like the door. If there's a door that's jammed and you go over try to open the door and you're like, it's not moving, it's jammed. Well, that means when you push on the door in the forward direction, where they're wedged together along that area where the door is meeting the wood, the frame, if you push forward, there must be some frictional force preventing that slippage of the door towards your chest in an equal amount at all times. You push a little harder, still doesn't budge, it means the friction force increased to match you. You push a little harder, still not moving, that means as soon as you push a little harder, the force of static friction increased to match you. It will always match you up until some point where it says, I can't go any more than that. You won. At that point, it gives way to motion, and the door will move in the direction you are pushing it. Usually the interesting part, the part of interest is what is that maximum amount of force between two objects that's considered static friction force? It's equal to the coefficient of static friction times the magnitude of the normal force. And I can put magnitude symbols around that just to say total quantity. It can be in any direction, and I'll talk about that in a minute, but the total quantity, total amount of maximum amount of force is equal to the coefficient of static friction, again, usually a number between 0 and 1 in most cases. So I've indicated that underneath, that mu s is usually in between 0 and 1 most of the time. I'll maybe make that comment, 99% of the time. There are some rare surfaces that actually provide coefficients that are really rough and really have a lot of friction and traction that can have coefficients higher than 1, but not usually. 99% of them are under 1. So this is the formula, and it's actually on the AP equation sheet. This is a formula that's actually on the AP equation sheet. So I'm going to show you how does that play out. If we're saying that the maximum static friction force is this equation, and in most AP problems, it's the same picture. It's a box sitting on a floor with somebody pushing it to the right. It could be to the left, but it's the same picture, 99%. They're not very creative with their at least with these multiple choice. They can be very creative with their free response questions. But multiple choice, they're usually pretty dull. This is what it looks like. The point is, we already know that the gravity is pulling down with gravity force, Earth's gravity force is pulling down with mg, and we already know that the normal force is upward in an equal amount to mg. So the normal force is mg in total amount, right? which means that if we're writing that with m and g in it, it's just equal to mu s times mg, where mg is the weight of the object. Remembering that if mu is a number between 0 and 1, like 0.6, then it's 60% of its weight, 50% of its weight if it's 0.5, 20% of its weight if it's 0.2 for the coefficient. So it's easy to calculate weight. You guys would all agree to that. M times g is pretty easy. And that if you know the coefficient, all you're really doing is multiplying it by mu. Just pointing out that this is the maximum amount. The maximum. Some students think that it's always that. And I get it, because maybe it's a hard concept. We'll try to explain that now. It's not always that. Let's return to the same idea. Let's say that in an example, let's say mu s is 0.7, the mass is whatever, 2 kilograms, g is 10. Well, and we're referring to this box, so we're referring to the area that's right underneath down here. And we say, all right, we can calculate that. That's mu times m times g. Just going to multiply those three numbers together. So it would be 0.7 times 2 times 10, like 20. 70% of 20 is 14. So I have a lot of students that could easily do that and say, okay, so it's 14 newtons. And I say, yep. And then I say, so how much frictional force is there now? No one's touching it. It's just a cup sitting there. They say it's 14 newtons. I can calculate it. Static friction force is 14 newtons. And I get it, because they're thinking if there's an equation, then you just plug it in and that's it. But I then challenge those students to say, but think about that for a minute. If nobody's touching this cup that's just sitting there, or a box that's just sitting there, and these forces are balanced, which we already agree on, and I then say, all right, you calculated the frictional force of 14 newtons. Which way is it? Nobody's touching that thing again. It's just sitting there on the floor. And then when I say, which way is it? They say, you scratch their head. Yeah, I don't know. Is it rightward? Is it leftward? I said, that should indicate to you already that there's a logic issue in this, because if nobody's touching it, there's no static friction force. Oh, eyebrows go up. Yeah, there's none. It's an important comment. There's no static friction force. If there are no forces attempting to cause, that are trying to make it move. If there's nothing trying to get this thing to move, like if there's a rock sitting on the floor, are there any forces trying to get it to move? You could say gravity's trying to get it to move, but the floor is going to prevent that. The floor is going to balance that out. Is there any possible unbalanced force? You'd be like, no. And so that's why there's no static friction force. If you then decided to come over to this block and push with same picture, same scenario, you decide to come over to the block. And again, this is the important part, because this is the logical side of this discussion. And this is where AP will come through strong. Their multiple choice questions, again, are usually deep level conceptual understanding. They know that students can do 0.7 times 2 times 10. And they say, that's not AP level. I agree with them. It's not. They're thinking, did they actually understand it, though? And that's the hardest part of teaching, of course. And that's what I'm trying to have you understand now, so you can better be able to attempt those questions. If you came over and pushed this, if we again calculated that the maximum static friction force is 14 newtons, and you push it with 3 newtons of force all of a sudden, but it doesn't move, there's plenty of room there. This static friction force can go all the way up to 14 newtons. If you're pushing with only 3 newtons, it will say, I can match that easily. My static friction force can easily match 3 newtons because I'm strong enough to go up to 14. In this scenario, on AP exam, they show a picture like this, and they show 3 newtons, knowing that the maximum amount is 14 newtons, and say, how much static friction force is there? They know half of the students will get it wrong because they'll say it's 14 newtons. They say, no, if there's only 3 newtons of trying to get it move, then the static friction force is matching that with 3, right? If you decide to push a little harder, you say, I'm going to beat this friction force. I'm going to push with 6 newtons of force, twice as much force. Static friction says, no problem. My little teeth that are kind of holding on to the little jagged areas underneath me can continue holding on. It's a locking effect that's going to maintain itself. This would be 6 newtons. This, let's take it to the limit. You decide to say, I'm going to push with 14 newtons of force. What happens? If you've calculated that the maximum amount of static friction force is 14, and you say, I'm actually going to push exactly with 14 newtons of force, the static friction force says, boy, you're tough. I can do that, but just barely. Oops. I can match you at 14 newtons. Still doesn't move, because what is the net force? Still 0. You decide to say, I'm going to push with 14.1 newtons. Now we've got a problem. If you're referring to trying to prevent this thing from moving, now you've got a problem. Because now if you're pushing forward with 14.1 newtons of force, the static friction force says, I can't go any more than that. You've maxed me out. I will still fight back with that 14 newtons that I have maxed out with, but I can't match you at 14.1. 14 is my maximum because mu times m times g underneath me comes out as 14 newtons. What will happen? It will move. What would the net force be in this scenario? 14.1 minus 14 equals 0.1 newtons. You mean there's an unbalanced amount of force? Yep, 0.1 newtons. What's going to happen? It's going to move in that direction, right? Motion occurs in the direction of the unbalanced amount of force, called the net force. What would the acceleration be? Well, then you say, but once it starts moving, now it's not static friction anymore. Now, is that block sliding along the table? Yep. So that's sliding friction? Yep. So if they're going to ask me questions about once it begins moving, I have to now start thinking about sliding friction. Did they give me the coefficient of sliding friction? Yep. Usually they give them both. They'd say, for example, mu k is 0.7 and mu s is 0.8. They're not always the same number. You should know that now. In fact, they're almost never the same number. I can pull up again a chart. I think I showed it to you some time ago when I taught you about the coefficient of sliding friction. And in that chart, it showed the coefficients of sliding friction and static friction for 2 different types of materials, like steel on steel or wood on wood. And I'll bring it up in a moment. You'll see they're never the same number. You'll also notice when we look at that, actually, I'll leave that. I'll let you guys look at that in a minute to come up with that. I will point out that the acceleration, if they asked about the acceleration, so motion occurs and it accelerates. At that point, with an amount of acceleration equal to F net over m, right? Where what would the net force be? Well, now that it's moving, now that this thing is actually moving to the right, there's now a force to the left, which is the kinetic friction force, no longer static friction, sliding friction. And if you kept on pulling forward with some force F, then the net force will be F minus FFK, right? It's just a difference between those two. If it's moving forward, then you're stronger than friction. You've proven you're the boss when it comes to the tug of war, which means that your amount of forward force is going to be more than anything friction can do, whether it's static or kinetic friction. And therefore, the amount of unbalanced force will be the difference between your pushing force and the static force, which is backwards the other way, divided by m, right? That's it. That's all I'm going to say really about static friction. I'm going to give you some problems where it plays out so you can see that, I'm gonna let you try it, and I am probably gonna put you in some breakout rooms. So with that said, if the two of you, I see he has it, which is fine, the two of you could take out your Chromebooks and log into my Meet. I'm gonna give you a problem that involves static friction, because that's a box that's has been needing to be checked off by me for a little while, and I knew I'd come back to it at the right time. I think today was totally fine to do that. Here's a special problem that uses what I've just taught you about. So I will, before I give you the special problem, I will tell you that to experimentally determine the coefficient of friction, I should say, the coefficient of static friction between two surfaces, let's just say you have wood and, I don't know, a quarter. And you want to know what is the coefficient of static friction between wood and a quarter. What kind of experiment could you design that would be able to help you experimentally answer that? And there's people that do this. This is potentially part of their job. If they're called material scientists, scientists that know all of the properties of materials, then this is something they're well familiar with, and they know someone contacts them, a business, that any question about any properties of that material and coefficients of friction would certainly be one of them. They'll know all about it. So what is μs between wood and a quarter? What experiment could you do? I'm going to tell you, and this experiment sometimes turns up. In fact, I'm not going to, do it underneath. So here's a plank of wood. Plank of wood, and then you rest your quarter on top. And you just lay it on the floor. What you then next do, this would be step one. Step two is you start to raise that up slowly into an incline. Step two, slowly raise plank to an angle that just starts to cause it motion. Just starts to cause motion. So what you would do is then raise it up to an angle. So this is going to involve the inclined plane, this special problem I'm going to have you work on. And if it starts to slide down, it starts to slide down. I'll draw that. There it goes. If this is true, if it does start to slide down this ramp, it means that the mg sine theta amount of force that's trying to pull it down the ramp was stronger than the static friction force, right? This would have been the maximum amount, that when you raised it up, at some angle, mg sine theta becomes sufficient enough, gravity's force down the incline becomes sufficient enough to say, I beat you. You can't go more than that. Motion will occur in the direction of my pull, which is down this ramp. So there's a net force in this scenario down the ramp. What would you next do? Now you would lower your ramp just a little bit. Then you would lower the ramp, lower ramp a tiny bit, so that the quarter doesn't slide. The quarter does not slide. But any any more angle would cause motion. So then lower the ramp a tiny bit, a little less than when you saw it just start to slide. Knowing that if you go up any more with that, it's going to slide. Lower it back down again so that it's just barely hanging on because the friction is like, I'm about to let go, but I'm maxed out. If you go any more, I'm letting go. At that point, which is now I'm drawing, that angle is called the critical angle, referenced for sure in the AP exam. The symbol for a critical angle is theta C. It's called the critical angle. Not my words, the words that all the world uses for this particular topic in physics, the critical angle. The critical angle is, again, that angle, the maximum angle where object still doesn't move. Any more, it's going to go. Called the critical angle. In that case, if you've so carefully gone up and down with the angle to feel like you got it just right, then how much force is pulling down the ramp? mg sine theta. Store that in your memory if you haven't already. The amount of force down a ramp due to gravity is mg sine theta. If it's not moving, then we would say that the net force is 0 if it's not moving. Right? It's not moving. That means there must be a force in the opposite direction of mg sine theta preventing this motion. Let's draw it in. Who would that be? It's not sliding friction. It's not sliding. Static friction. So I'll label it as FFS max. If that's true, that means those two forces must be equal in amount. These are equal, right? Because you're at that point where it's like, it's about to go. The amount of force down the ramp is exactly equal to the frictional force up the ramp. Don't go any more, gravity will win. But stay at that one moment, that critical angle, those two forces are equal. This means, again, at the critical angle, at theta C, the x component of gravity is exactly equal to the maximum static friction force in magnitude. Because in a lot of cases, direction doesn't matter. Don't worry about direction. Sometimes you'll have to again, but in a lot of physics where it doesn't matter. Just know that this amount of force can be represented with this equation. This amount of force can be represented with this equation. And if in the case that they're equal, you just set them equal. Don't worry about was it plus, is it minus. Don't worry about that. Just this amount is equal to this amount. Keep it simple. It's already complicated. Physics is already complicated. Keep it simple if you can. What is the equation for FGX? mg sine theta. Because we stored that to our memory. What is the equation for the static friction force? The coefficient of static friction times the normal force. Store that to your memory if you haven't already. Know that any friction force is always the coefficient of that friction times the normal force. Since we're talking static friction force, it has to be the coefficient of static friction. So now we're on a ramp and we have to think about the normal force? Yeah, unfortunately. That makes it a little more challenging, but doable. Think to yourself, what would the expression be for Fn, which is in this direction? Because you need it. You need to put it in right here. And if you don't know what that expression is, you can't move forward. What would Fn be equal to? Same idea, remember, that mg pulls down here. Then there's an amount of gravity force that we call Fgy. That's actually mg cos theta. And the amount of force that pulls it down the ramp is mg sine theta, where theta is in here. So that normal force is perfectly balanced with mg cos theta. Yep, mg cos theta. Mg cos, because they're balanced, right? Along that axis, these are balanced. So mg cos theta is equal to Fn. In the inclined plane problem, Fn is equal to mg cos theta. If the ramp, remember, is lowered all the way down to the flat floor, then the angle would be 0 degrees. If you plug in cosine of 0, some of you may know that cosine of 0 is actually 1. And that means if you lowered the plank down to flat surface and then asked, can we still use this formula, mg cos theta, to determine the normal force still when it's flat on the floor? I'd say, yeah, that's a 0 degree ramp if you want to call it that. Cosine of 0 is 1. The normal force is just mg. Ah, that's nice. That works. That brings us back to just introductory physics. Mg down, mg up. Yeah, physics can be nice like that. So let's finish this idea, and then I'm going to give you the problem. I'm close. I'm right there at that moment. Trying to pull it all together. Mg sine theta, as I said, I'm just rewriting what I had up there, is equal to mu s times, now we got to plug in Fn. Mg cos theta. This is called equilibrium. And since it's not moving, we call it blank equilibrium. We call it static equilibrium. Remembering that static equilibrium means that there's a balance of forces, that there's no net force. And you're like, it all makes sense because we already said in our original picture that mg sine theta is equal to the frictional force up. Those are balanced. And then the vertical direction, at least vertically this way, the normal force that goes up is balanced with mg cos theta. Everything's balanced, right? So that's called the static equilibrium. In APA physics free response, they might say, write the static equilibrium equation that represents and models this. This is what they'd be looking for, 5 points. I don't think they'd expect that you memorize it. I think that that's why I have to take the time to show you this stuff, because students are eventually learning the skills that at the end of the year, I can actually work this out my own. I don't have to try to memorize it, because at some point students realize there's no way. I can't memorize all of this stuff. I'm like, yep, absolutely. You're not going to do it unless you're literally a computer. I've never met any student in 15 years that can memorize all of this, not one. So you learn the steps, and sometimes you can figure it out on the fly. My question to you, and I'm going to put you in a breakout room, is to solve this equation for mu s, because that's what the experiment usually is done for in the first place. That's why they do it. They find this critical angle because they know that there's some math available where they can plug things in and determine the coefficient of static friction between those two types of material. In this case, would be quarter and plank wood. To solve this equation, I'm going to pop you into some rooms. I'm going to give you about, in between, I don't know, 10 minutes might be too much, 7 or 8 minutes. The formula that you get, US equals, is on the AP exam almost every year. Maybe for 1 or 2 problems. So one of those check boxes. All right. Oops, back, and I went back again. Go back here. Let me drag this down. Let me say breakout to how many people? 1, 2, 3, 4, 5, 6, 7, 8, 9. So let's do, well, 3 of 3, 3 and 3. That worked. That nice balance. All right. You guys have any questions about what I'm asking you to try? You can work on it on your own for a minute if you want, but then talk to each other. Say, hey, would you figure it out? And if you, I'm not stuck. How did you do that? That's the question. What is that equation solved for mu s? One more time, I'll put it right here before we break out. This is the formula. Mg sine theta, that represents the amount of gravity force pulling down the ramp, is equal to mu s times mg cos theta. That's the amount of static friction force up the ramp. And they're perfectly balanced. Solve this from us. Little geometry challenge. All right, I'll pop in a minute and see how you're doing. Is it too cold in here? Cool, but not too cold? Just a quick question to you guys. Does it always put you in the same group? Or is it different sometimes when it puts the groups? Is it always the same? What is it? Sometimes it's different. Okay. Yeah, it's supposed to be. It's supposed to be random. I'm starting to get the feeling that it was the same. All right, welcome back, everybody. I'm going to go over that question with you now, if I could. I may need to represent my screen. Yep. Okay. Let's see. Let's see what we got here. We had down the ramp was mg sine theta equal to up the ramp, which is mu s times mg cos theta, where the left side represents fgx and the right side represents the static friction force. Technically, the maximum, it's been maxed out. That's the assumption. You've maxed it out. So they're equal. All right, so then we write that logic into a mathematical equation. Mg sine theta equals mu s mg cos theta. The first thing that pops out is that m and m can be canceled by dividing both sides by m. G and g can cancel by dividing both sides by g, because you can do anything to an equation as long as you do it to both sides equally, right? Of course. So what are we left with? We're left with sine theta is equal to mu s times cos theta. Now this, if there is a stopping point for students, it might be here. If not, they would know, okay, well, let's at least just divide over by cos theta to both sides. And we end up with an equation that says the coefficient of static friction is equal to sine theta divided by cos theta. Now, for the students that memorize all the trig identities, and you're out there, and I'm sure it's not all of you, but you're out there, you might remember that sine over cosine actually is some other trig function. If you didn't remember, and that would be just teaching students by memory, which I don't recommend, you could technically prove it to yourself, what this turns out to be. You could say, well, sine theta we know is opposite over hypotenuse divided by, right? Cos theta we know is adjacent over hypotenuse, right? Okay, so I've got a fraction divided by a fraction. We call that a complex fraction. I know that if I had to do 3/4 divided by 5/3, that I can do that by just reciprocating 5/3 and multiplying 3/4 times 3 over 5, and then just multiplying through. You know that, that's true. So let's try that over here. What's the reciprocal of adjacent over hypotenuse? Hypotenuse over adjacent. I now see that hypotenuse and hypotenuse cancel, leaving 1 behind. So opposite times 1 is opposite. 1 times adjacent is adjacent. So we're left with opposite over adjacent. Wait a minute, isn't that tangent? It is. It is tangent. Because tangent of theta is equal to opposite over adjacent. What does that tell us? It tells us that the physics equation that you'll want to know for this particular very specific problem is that mu s is equal to tangent of not just any angle, the critical angle. Because we derived this question, remember that theta really was that very specific angle where you knew if you went just a hair more, it was going to slip. So you wouldn't want to just put theta there. And in a physics exam, they'd have a C there to indicate that's that critical angle. That's the, I'll make comment there. That's the critical angle. Why is this useful? Because if you did this experiment and you found that exact angle right where it was about to slip, you could just measure it with a protractor. One way, right? That means once, so let's just say, for example, we did it like that. Let's say we go like this. We see it just about to slip, but not quite. And we measure this to be, I don't know, 60 degrees. And this is at the critical angle again. Experimentally, they look at each other and say, all right, let's calculate the coefficient of friction between, well, I guess it was the plank of wood and the quarter. All right? We know our physics formulas, mu s will be equal to tangent of that critical angle. Therefore, if we measured it at 60 degrees, we would just do tangent of 60 on a calculator. Here's my calculator. Tangent of 60, making sure that I'm in degree mode. enter, I get 1.73. Greater than 1. But let's be honest, that's not a 60-degree angle, right? What I just drew there is not a 60. Like if I was actually drawing a 60-degree angle, it's more like, maybe even more than that, but that's more like a 60-degree angle. That thing's holding on at that angle. Wow, that's some serious stickiness underneath there. That's some serious traction. Therefore, the coefficient of friction is unusually high because most things would slip by way before 60 degrees. So that's why it's greater than 1. What if we looked at 45 degrees? Kind of the way I drew it before. What if the critical angle is 45 degrees? Then we would say the coefficient of static friction, if it was just about to slip at the 45-degree angle, would be tangent of 45. Wait, 45? That's our 45, 45, 90 triangle, isn't it? It is. Isn't that the 1, 1, root 2? It is. So tangent is opposite over adjacent. That's 1 over 1, right? Because only the hypotenuse is root 2. I'd say that's right. So that means tangent of 45 is 1 over 1 is 1. That's right. So therefore, the coefficient of static friction is just 1.0. Yep. What that tells us is that anything that can hold on just due to static friction at 45 degrees or above has a coefficient of static friction that's at least 1 if it's at 45 degrees. If it can hold on still at 60 degrees, wow, it's 1.73. What if it could go to 98 or 88 degrees? Oh my God. Think still, you put some glue in there or something. I don't know. If it's glue, then we're not talking static. Glue is not static friction. Static friction is a natural traction effect. But let's just say there's some crazy 88-degree angle and it's still holding on. US is tangent of 88. Holy moly, 28.6. I don't think there's anything that can do that. So what's worth commenting on? I think what's worth commenting on is that mu s, when mu s is between 0 and 1, the critical angle is between 0 degrees and 45 degrees. Right? That's what we were just showing, that when it was a 45-degree angle, the coefficient of friction was 1.0, if you want to call it that, 1.0. If the critical angle is greater than 45 degrees, then the coefficient of static friction is greater than 1. Right? Tells you that 45-degree angle is experimentally an important angle. If they were trying to, decide, all right, we're trying to test samples to see if we can get things that are unusually high friction coefficients, we would want to hone in on those samples that were able to hold on beyond 45 degrees. We right away can make a pile and say these things are all going to have coefficients of friction higher than 1. So that's worth commenting on and worth knowing. I'm going to show you one other thing. If I were to show you this, I just posted it in Google Classroom. This chart, you can see on your own, but I'm just presenting it. That this is, again, the coefficient of static friction and kinetic friction for a variety of materials. Remember, it makes no sense to say wood has a coefficient of friction of 0.5. Do you mean wood on wood? Because friction requires two things to rub against each other, or at least to be in contact with each other. So you can't say ice has a coefficient of friction of such and such, or wood has a, no. Notice that the list says steel on steel, Teflon on steel, wood on wood. Experimentally, it makes sense. You need two materials. You'll notice that one column provides the coefficient of static friction. That's the left side, mu s. You'll see that the right side is the coefficient of kinetic friction, mu k. You'll notice that all of those values are less than 1. Another worth noting. What's the one other thing that pops out to you when you compare the numbers in the coefficient of static friction column to the numbers in the kinetic friction column? Is there any other really good observation you can make that tells me what one last primary difference is between the left column and the right column, numerically? There is a pattern there. I don't have to call it a pattern, but something that's true. Yeah. Yep, good job. Good job, Kyle. kinetic friction is almost always less than the static friction coefficient. Or I could say it the other way. The coefficient of static friction, the one we've been talking about, is almost always more than the coefficient of kinetic friction for the same two surfaces. One was greater than 0.7. 0.7 was greater than 0.5. 0.5 for 0.3. And you can look through them. It's always true. Worth noting down, they sometimes have that. I recommend you write that. Coefficient of static friction is almost always, in fact, it might be always. I don't know if I've ever heard of an exception to that. Mu s is greater than mu k. Let's just go for it in all cases. I honestly don't know that I've ever heard of an example where that's not true. The last comment is, why would that be the case? The reason is because when you're looking at these microscopic hills and valleys like I've talked about, if they're at rest, if the thing is at rest and we're talking static friction, these really get to sit in nice and tight and provide a nice tight locking mechanism. So that means the static friction force is going to be really large. So remember that the static friction force compared to the kinetic friction force, they're the same format, mu s versus mu k times the normal force. If we're realizing that the static friction coefficient is almost always greater than the kinetic coefficient, then aren't we saying that the static friction force is almost always greater than the kinetic friction force? Yes, that is what we're saying. That means for two surfaces, you'll always get more static friction force between the two surfaces than you would out of any sliding occurring between the two. So I'm going to note that here. FFS is greater than the kinetic friction force. Sometimes comes through on a multiple choice concept question. These two sometimes come through on multiple choice questions. So what I was pointing out is the reason is that, again, those things, when they're at rest, it's a tight fit. And that tight fit causes just more friction, more traction. On the other hand, when something is sliding, if this thing was sliding along like this, there's not a tight fit. It's a bumpity, bumpity, bumpity. It's skipping along like a rock along a pond. Ba-dum, 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 ba-dum. Each little ba-dump still slows the object down that's sliding, but it's not as much of an effect as letting it be at rest, letting the full weight of the object press it into the bottom of this thing that's down here, causing that nice tight fit where, wow, now you got a lot more friction to deal with. Sliding friction is therefore always less than static friction because the bumpty effect is not as strong of an effect as the tight fit effect, if that makes sense. All right, I'm going to give you one last thing that at least jot down that you can work on for homework relating to this. And then I'm probably going to add a couple others, but similar to this question. We're almost out of time. Losing my focus. I'm not coming back. There we go. So the question is, if the coefficient of static friction between two surfaces is 0.36. I just totally made that up because it doesn't really matter what the number is. If the coefficient of static friction between two surfaces is 0.36, what would the critical angle be? Critical angle, remember, is represented in most physics books as theta c, meaning that we're assuming we're doing the experiment he talked about. This is surface 1 and this plank is surface 2, the two surfaces, and we're referring to the critical angle as a little picture there. Because technically, again, if we have that formula, mu s equals tangent of the critical angle, we should be able to use it in two directions. All formulas can work forward and backwards. So in the last case, we said we could plug theta in, the critical angle, to determine mu. Well, what would the opposite be? If we know what mu is, the coefficient of that, can we predict exactly what that slipping angle would be? Which, by the way, for avalanches, is actually very important. Because when an avalanche happens, it's because the static friction force is not strong enough to uphold the weight of the snow, and slippage occurs. Now you got real issues. Obviously, people can die. So predicting what the critical angle is, depending on this textural combination of two surfaces, in some cases can be extremely important. So that's why my question is the reverse question of what we did before. I'll post this in Google Classroom. I'm going to actually probably type it up. I'm going to add some more relating to friction and maybe a few others. So just keep an eye on Google Classroom, but this will be one of them. In this case, you know the coefficient of static friction. What would the critical angle be? It's still the same formula, just I need to know that students know how to use this and know how to use it in both directions. All right, I think we're pretty much out of time. Yeah, we got like 30 seconds left. Let me click back over here. My hope was that I covered most of static friction today. I had to do that. At least earned one day because I can't go through and say I never talked about static friction. It's an important part of what you have to learn. So most of what I gave you is mostly the total amount that I need to give you for the most part. We'll see that it does turn up later in the year, I'm sure. Everything kind of rears its ugly head at various points through the year. And you're like, oh, there it is again. Well, yeah, it pops up at different topics. So we'll see it again. And I'll be talking a little bit more about it with you when I see you next, when we review this assignment. Again, that's the first problem. I'll post it. I'm going to add a few more. Not a lot more because I see it tomorrow, but maybe a total of 20 to 30 minutes, a couple problems. And then I'll plan to see you guys tomorrow. Amazingly, it's Friday already. Weeks are going by fast, at least they are for me. All right, I'm going to say goodbye to you guys at home. Enjoy the rest of the day. If you have any questions, you email me again. If you want any help, reach out to me. Tell me you want some help. It can be any day, Monday through Friday. And I can certainly give you a virtual meeting to help you prepare for anything or help you review once a week. Again, there will be a quiz probably midweek. I don't meet you midweek, so it'd have to be either Tuesday or Thursday. It'll probably be on Thursday. That gives us one more day, Tuesday. But I'll post that as well. All right, if there's no questions from anybody at home. All right, have a great day, everybody.